I hope that you've been enjoying the conference so far and Montreal has been treating you well. It is my pleasure to introduce Dr. Francesca Dominici, our plenary speaker this morning. Francesca is the co-director of the Harvard Data Science Initiative at the Harvard University and the Clarence James Gamble Professor of Biostatistics, Population and Data Science at the Harvard T.H. Chan School of Public Health. Her areas of expertise include causal inference, machine learning, and Bayesian statistics with applications in environmental health sciences, climate change, and biomedical sciences. Francesca's work has informed the scientific community and policymakers on the adverse health effects of air pollution, noise pollution, and climate change. She has published extensively and was recognized in the Thomson Reuters 2019 list of the most highly cited researchers, ranking in the top 1% of cited scientists in her field. Please join me in welcoming Francesca.
Well, good morning. Thank you. First of all, I want to say thank you very much for inviting me. It's a pleasure to be here. It's a pleasure to be here in person, see so many friends. So thank you, and thank you for being up. I would say for a Bayesian conference, 9 a.m. is really early, so thank you for showing up. So this is work that is actually not joint, but I would say I should give the total credit of what I'm talking about to my colleagues, Zhao Hu, Boyu Ren, Daniel Brown, Natesh Pillai, and Fabrizia Meali, and then many, many others to which I'm going to give full credit. This is I'll tell you a little bit of a story about data science and Bayesian statistics and environmental policy throughout the transition from Trump to the Biden administration. And so when you're really trying to make big changes, it takes a village, right? It actually takes probably hundreds of statisticians. So by no means this is only my work. So let's start with the background. This is like, I'm gonna have my talk is a little bit as one of these TV series, right? Where season 1, season 2, and season 3. And there are multiple episodes within each season. So let's start with the background. So the background, let me start with actually good news, right? Let's talk about good news. The good news is that data science has really provided an enormous positive impact in society and in public health because thanks to the Cleaner Act. The Cleaner Act is basically saying that if we find evidence that the current level of air pollution in the air is still harmful to human health, we need to lower the safety standard even further. So that means actually that by looking at the data, by looking at the data science, and by looking at the evidence, we can make a policy change. And as a result, as you can see from this slide, we are all breathing cleaner air. So on the left, there are levels of primary pollutants in the air in the last 20 years. You see that they're going down, and you're seeing that the skyline are cleaner. So that is excellent news. The question is, are we breathing air that is cleaner enough that are not providing any adverse health effect? Because again, the Cleaner Act say that even if these levels are lower, but the question is, are low enough, right? The other thing I wanted to mention, next, okay, is although I will focus the statistical and Bayesian and everything in the context of assessing the health effects of air pollution, there are two main points I want to make. One is that if we target and reduce exposure to air pollution, we are basically targeting greenhouse gases emission as well. And the reason is because the main sources of fine particulate matter and air pollution are the same main sources of greenhouse gases emission. So you have actually this double benefit, right? You reduce air pollution in the air, you are targeting greenhouse gases, and you're also basically tackling climate change. That's point number one. Point number two is, although I'm going to talk about the statistical methodology and development in the context of air pollution exposure, we are working on applying and developing methodology not only in the context of air pollution exposure, but in the context of a large set of climate change-related exposure, like heat, wildfires, droughts, tropical cyclones. So in a statistics, so these are just different types of exposure variable, right? So I'm gonna tell you the story in the context of air pollution, but just keep in mind that we have the data and we are developing the methodology, not only thinking about the public health consequence of air pollution exposure to impact regulation and therefore impact climate change, but also in the context of wildfire exposure, in the context of heat, and the context of tropical cyclones, and so on. So from a statistical viewpoint, I want to be very specific and very rigorous about the scientific question. Okay? And so I'm going to really focus this talk on really addressing a $1 trillion scientific question. And the $1 trillion scientific question is, currently in the United States, the national ambient air quality standard for fine particulate matter are set to 12 microgram per cubic meter. And it's very clear scientific question. If you're breathing level of air pollution, level of fine particulate matter below 12 microgram per cubic meter, are we still seeing adverse health effect? If the answer is yes, by the Clean Air Act, they have to lower the national ambient air quality. And the benefit of lowering national ambient air quality standard have been estimated in the context of trillions of dollars, right? There is also cost associated with lowering the national ambient air quality standard because it means implementing costly regulation. We can all discuss, that's going to be a different talk about the cost-benefit analysis of the Clean Air Act, but believe me, we are talking about $3 million, several $1 trillion question, right? So this is the question. Now, there is no data science, in my opinion, without data, okay? So when we talk about machine learning and matching and Bayesian and causal inference, the first thing that we have to think about, do we have enough data? Do we have the best possible data? And in all of my work, I've been spending my last 20 years really working and raising funds and, in all of what I call it the data engineering part. I haven't done it by myself. I know nothing about data engineering, but I think I understand that extremely important to collect the largest possible source of data. And so we've been building organically over time. And as you know, there is no funding for building data platform or not direct funding. So in building the large data platform, I would say in the world where we basically gather heterogeneous data sources on exposure to air pollution and climate-related exposure, risk factors, the urban environment, and assessing the health impact. So let me tell you a little bit more about the data. So we, in the United States, for people that live and breathe in the United States, we don't have a national health insurance. Yeah, I know we're pretty jealous about being Canada and Europe, but there is a kind of health insurance in the United States, which is the Medicare system. So when you're turning older than 65, you get into the Medicare system. And by the way, even if you have additional health insurance, you are in the Medicare system. So when I'm looking at everyone around you, if you are older than 65, I have a bad news for you, I have your data, okay? I cannot identify you, but I do have your data. So it's 95% of the population older than 65. They enter in the cohort. We know where they live by zip code of residence. We know age, gender, or race. We know whether or not they're getting supplemental health insurance. So we know whether or not they're in Medicaid, which is a surrogate of lower socioeconomic status. And then we know every single hospitalization and for which cause. And then we also know their date of death. By the way, the Medicare files, you can purchase prescription drugs, you can purchase doctor visit. It's actually really, really rich. It's not super costly, the files, but managing the files are very costly. So we have been, basically, I will call it, this is an open cohort, right? Every year, as a new group of young Americans become 65 years old, they show up in my cohort, and then I can follow them over time. I know their zip code of residence. This is really important because then I can link to their environmental exposure. And then we have some individual level characteristics. So there is a giant amount of work behind the scene of harmonizing, integrating the heterogeneous sources of data. By the way, here's an advertisement. If there are people that are really good and want to do data engineering and are interested in this problem, please let me know. We are hiring data engineers all the time because we need as much as help as we need on this type of analysis. So this is how, at the very high level, the research data platform looks like. So we have exposure to air pollution, exposure to methane, we know where fracking sites are, we have exposure to heat, we have exposure to tropical cyclones, all of that. So this is like a bucket, I call it exposures, right? So these are spatial temporal data. I'll tell you a little bit more for the last 20 years. And then we have a bucket of health outcomes that comes from the Medicare, so we can link to health data. And then we have a bucket that we call the confounders, right? So risk factor, behavioral factors, census data. None of this is optimal, but it's the best that we can do and the best that we can continue to do on harvesting all of government data sources that are available, both they're publicly available or not that we buy. So let me talk about the first challenge. So this is the map in the United States where the air pollution levels are monitored, right? And so you can see that there are several monitoring stations in the United States. I think it's monitored pretty well, but it's not monitored everywhere, right? Remember that we have health data for the whole population, so for every single zip code in the United States. We have a national coverage. So my colleague have been developing machine learning approaches, and I'm not going to go very much into the rigors of this, but there is a lot of literature, which basically what we do is we take satellite images that have an imprecise measure of air pollution. It's called aerosol optical depth. We take output of atmospheric chemistry model. We have weather data, land use data, a bunch of data. We train a model also on the monitoring station, and then we estimate exposure to fine particulate matter, 1 kilometer grid for all the continental United States. There is an entire field, fantastic field, on deep learning, ensemble learning, which is basically Bayesian model averaging, and this is a prediction problem, right? So you can have as many machine learning model that you want. I don't need to interpret this model. The only thing I needed is to get the best possible prediction. So here is an example of a snapshot of exposure to fine particulate matter in a particular year. There is more and more work is going, which by no means I am leading. My colleagues are leading. They are doing really phenomenal work in getting very precise spatially resolution exposure to, in this case, this is a map of elemental carbon for all the continental United States. And you can see how in some of the urban area, really we can get very, very, very precise. And these models are very validated and so on. So this is an entire field that I am kind of leveraging. They're working in my team, and this is really about machine learning and prediction, and by the way, quantifying the uncertainty on this prediction, right? So there is machine learning with spatial varying coefficients and so on. But the bottom line is, what I'm saying in my talk is that we can leverage this phenomenal prediction, a high level of spatial resolution, to link it to the health outcome. So let me start with the first part, okay? This is season one. Season one is work that we have done a few years ago in 2017, where we had done I would call it the vanilla statistical analysis. So we now have exposure to air pollution for the continental United States. So we have a cohort of 67 million Americans, and we have confounding factor, and then we said, okay, let's ask the question, are exposure to air pollution even below 12 micrograms per cubic meter harmful to human health? And we addressed this question by doing a survival analysis and a Poisson regression. So we published this paper in 2017 in the New England Journal of Medicine. This was really a huge study, right? Because then, again, from changing policy, you need to say, we studied every single or 97% of the study population, and we did find that even if you breathe air pollution level below the national ambient air quality standard, is harmful. And so in this way, we are kind of trying to address the $3 million question and say, well, you have to lower the standard. So just to give you a sense of the study population for a moment, so this is 60 million people. We have 460 million person years into running this Cox model. We ran this Cox model, by the way, on a Christmas Eve taking all of the Harvard supercomputer under control. It was a very interesting experience. And it's funny because this was in 2017, and now we can run the same model in 30 minutes, right? So from 2017 to 2022 is actually amazing. Like, well, first of all, we are doing better job, as I'll show you later, but also in terms of computational scalability. So now also what's important here, if you look at the last column of this table, we have 32 million American and 247 million observation of people that are breathing level of air pollution below 12 microgram per cubic meter, right? So we have a ton of data for people that are breathing cleaner air or safe air, right? And so the question is, again, like, do we find that this is a harmful effect? Well, we did find there is an harmful effect, not only for all ranges, but actually that we found the effect was even more harmful at lower level. So this is just one of, you can look at the paper, very straightforward, but basically the horizontal line is at the national average, and so we found that for 10 units increase in fine particulate matter, that you have been exposed in the previous year, it was a 7.3% increase in mortality. And then what was very striking was a much higher risk for the Afro-American population, also much higher risk for the Asian and Hispanic, a little bit higher risk for people that were eligible for Medicaid. Again, vanilla regression analysis, time to event analysis, to look at whether a long-term exposure to air pollution is associated with time to death, associated, control for a series of confounding factors in a traditional regression model. It turned out that you don't need to do a survival analysis. You can reparameterize as a Poisson regression analysis. It's much more computational, effective, efficient. You get the same results, but it's like vanilla regression, okay? Well, when we published during the Trump administration, as you can imagine, this is a $3 million question. There's a New England Journal of Medicine paper, 470 million observation. It got a lot of press attention. And actually, Senator Booker used the paper actually to not point to some of the favorite Trump candidates to the Environmental Protection Agency, attacking them. They have really know nothing about data science, and they don't know nothing about air pollution and so on. So, it got a tremendous attention. And of course, it also got a lot of attention from the friends of the Trump administration. This guy, Steve Malloy, that has, by the way, if you want to have some fun, just go on the Junk Science website and Google my name and some of my colleagues. You will find a lot of very interesting things, like I scare for pollution. And then a friend of our group is like Tony Cox, and basically suing the editor of the New England Journal of Medicine for scientific misconduct because he has published this study. But one thing which was very interesting about that, this phenomenon was one of the attack they had, which, by the way, I kind of agree now, was like, well, this is all CRAP. This is really BS because it's just a regression model, so you cannot assess causality. Right? So how do you really know it's our pollution? And we should just dismiss the entire evidence because all is about assessing causality. You need to say that air pollution caused that, and these regression models are not good enough. Of course, we know it's much more subtle than that, but that opened the world to the opportunity to really thinking about causal inference and say, well, now there is an entire field, as we have been two wonderful sessions here on causal inference, so why don't we leverage and develop new approaches to thinking about better assess for measured confounding and unmeasured confounding. By the way, in all of this talk, I'm going to address issues of measured confounding in causal inference. There is an entire field which is equally important for addressing unmeasured confounding, which I'm not going to be able to talk about. So that's we'll talk with the second episode. So now we say, okay, now let's think about causal inference method to analyze the same database. Actually, to analyze the database is even bigger, right? So how we do causal inference methodology? So first of all, also, let me say that since then, causal inference is playing a huge role in environmental policy and in climate policy. So right now, the EPA is basically, through the new administration, is trying to relook at whether or not lowering the National Environmental Quality Standard. There are actually multiple panels of the National Academy of Science really thinking about how you assess causality in the context of environmental policy and climate. And climate also, as you know, there is a lot about to do with fingerprinting and attribution, which is another way to think about causality. So there is really a huge opportunity for us as a field to really thinking about our causal inference in this type of problem. So let me give you the 101 idea of matching. And many of you are expert in causal inference much more than I am. And again, there have been 2 fantastic sessions. So for people that are very familiar with this, you can just take a short nap. But basically, the fundamental idea of matching, again, it's a huge field. I'm just citing one of the many textbooks by Don Rubin and Paul Rosenbaum. I mean, there are hundreds of books. But I just want to give you a cartoon and just to think what's really the fundamental idea, 101, because then if you miss the next 40 minutes of my talk, it's okay, you got the idea. So basically, let's assume that you have only 2 geographical locations, right, in the United States. You have Steubenville, Ohio, an industrial city, high level of pollution, and you have Portage, Wisconsin, that is much cleaner. In Steubenville, Ohio, you have people that smoke, people don't smoke, people that are rich, people that are poor, right? So I'm going to identify Jane. Jane is Jane lives in Steubenville, Ohio. I've been breathing, poor Jane, very polluted air for all her lifetime. She has a low education, but she's not a smoker, okay? This is Jane. And Jane, let's say that Jane dies at 75-year-old, okay? So I know everything about Jane. I know everything. I have a lot of information about Jane, right? And she's been breathing pollution, and she's dying at 75. What I want to know is how much longer Jane would have lived, Jane herself, if instead of living in Steubenville, Ohio, she would have lived in Portage and breathing clean air. That's the counterfactual question, right? So how do I figure out this counterfactual for Jane? Okay? Well, I figure it out, I hypothetically find the twin sister of Jane. Let's say that Jane has a twin sister, right? It's exactly as Jane, but is living in Portage, right? And so I can see that the only difference between Jane and twin sister, they've been breathing different level of pollution, okay? So we could do that actually with twins, but we don't always have twins, but we don't have twins, but we have 500 million observations. So I can find in Portage all of these women, they are similar as possible as Jane. Same socioeconomic status, they don't smoke, they do similar things, right? But they've been living in Portage. And the average age of they died is 80, right? This is how I impute the missing counterfactual for Jane in Steubenville, Ohio. Okay, that's really the fundamental idea. And the next 20 minutes, I'm just going to give you much more complicated way to impute the missing counterfactual, because we not only don't have 2 locations, but we have every single location in the United States, right? And we don't have any binary exposure. A lot of Bayesian causal inference is about are you getting the treatment or not getting a treatment, but we have a continuous exposure. We have different level of pollution. So that's really what it's about. So to work with my fantastic colleagues, Zhao Hu and Danielle Brown, we basically did a causal inference analysis and come up with a new methodology to do exact matching in the context of air pollution to assess the causal effect of a fine particulate matter on mortality. So same database that we analyzed in the New England Journal of Medicine, we just updated to more recent data. And so basically same information. We now have 38 million Americans that are living a level below 12 microgram per cubic meter. These are all of the data that we have. You can see we use this machine learning model to estimate exposure to air pollution. The map on the left is the level of pollution in 2000. The map on the right is the level of pollution in 2016. So when you're thinking about causal inference, the most important place, which what we have been discussing, is that confounding, right? Confounding is the largest threat to the validity of this study. So when you do a regression analysis, you're just for confounding by including this covariate into your regression model. When you do causal inference, you're trying to do something better, which is by by matching. What this plot shows, in the context of a continuous exposure, when we think about matching and when we're thinking about covariate balance, we really mean talk about correlation. So what this plot shows on the right is that the absolute correlation between the level of PM2.5 and many other additional covariates, like traffic pollution, humidity, percentage black in that population, temperature, education, right? So you can see that for many covariates, there is, they can get higher correlation between each of these covariates and PM2.5. We need to break that correlation by doing matching. So in this way, we can actually almost approximate the randomized experiment. Ultimately, the goal, the dream will be, can you randomize people around the United States of breathing different level of pollution? Of course, we'll never be able to do that, but that's what is the power of causal inference, that we can actually, by matching, we can approximate the randomized experiment. So we did analysis by, again, feeding a traditional regression model and then coming up with a new approach for doing exact matching using a generalized propensity score, which I'm going to tell you in a moment. And so we implemented the matching with generalized propensity score, doing a matching, weighting, and an adjustment. And just think about this is a causal inference analysis of 550 million observations. So it's not trivial. So a small parenthesis for people that are not very familiar with causal inference. In causal inference, when you're thinking about matching, and we are thinking about binary treatment, so you're always matching by, we call it a propensity score. If your treatment, in this context exposure, is continuous, then you are matching by what's called the generalized propensity score. And the generalized propensity score is basically an estimate of the conditional distribution of your exposure, W, then this context is continuous, and a bunch of covariate. We are going to estimate this propensity score using machine learning. You can do it any way that you want, but you want to be as flexible as possible. So then instead of matching exactly by each single covariate, you're matching by this score. By the way, there is a huge literature on exact matching with respect to the generalized propensity score, with respect to every single covariate. This is something that by no means I'm not the only one doing this work. So Zhao and colleagues, this is a paper is under final review for JASA, finger crossed. By the way, everything about here, the code and the data are publicly available, so you can download and play with that. So basically come up with, it was a former PhD student of mine, and to come up with an exact matching procedure to basically create a new data set, which actually, if you just follow the last row, basically the idea is to come up with a new data set of number of exposure level, L, times the number of subject, because basically for every subject and for every exposure level, we need to estimate their counterfactual outcome with respect to all of the other potential observed levels of covariates. So basically, we wanted to construct a matched data set that approximates a randomized experiment by achieving good covariance balance, in other words, by breaking the correlation between every potential confounder and exposure. And so, in the continuous exposure setting, it's much more complicated and just annoying than in a binary, but the concepts are pretty much the same. So the idea is basically that the closeness of exposure level guarantees that the matched unit is a valid representation of the observation for a particular exposure level, where the closeness of the generalized propensity score ensures that we are probably adjusting for confounding. So basically, coming back to the Jane, I need to figure out the potential outcome for Jane, not only at the level of exposure for in Wisconsin or in Oregon, but for every single zip code in the United States. So this is a giant matrix. L is all of the possible exposure that we categorize by a very fine level, and N is the number of units in the data set. So as you can see, we were able to achieve good covariance balance. So both on the panel on the left and the panel on the right are how we are breaking the correlation between any potential confounders in PM2.5 for all of the exposure level, and on the right for the exposure level below 12. And so the red dots are the observed correlation in the data set, and the green dots are the observed correlation in the matched data set. okay? So we have created a new data set of all match unit. And again, we're not looking at the outcome yet, and we're just recalculating this correlation. And you can see this is very powerful, in my opinion, because basically, again, this is like also the power of having a lot of data. There is no correlation anymore between any of the potential confounders and PM 2.5. And so it's the best we can do, I think, in approximating a randomized experiment. So we assume for a moment a linear model, and on the left, these are the estimates of the effect of PM 2.5 on mortality, both using the two regression approaches and using the causal inference approach. It's actually pretty interesting that when you look at PM 2.5 for the whole range, actually they don't change too much. So again, like, this silly vanilla, kind of stupid regression actually worked pretty well. Now, it's true, though, that when you look at the level of below 12 microgram per cubic meter, and you are comparing the approaches done on causal inferences versus the one on the regression, you have smaller estimates. But still, the panel on the right is actually the most important from policy viewpoint, because you have that even if you restrict the analysis only to people that are breathing levels of pollution below 12 microgram per cubic meter, there is evidence of a statistical significant association between PM 2.5 and mortality is actually higher than for the whole range. And actually that has been confirmed in studies in Europe and in Canada. And so basically what we found is that lowering their quality standards from 12 to 10, so only to 2, we will save 140,000 lives per decade. But now, this is still not good enough, because really what we did and what you need to do in this context from a statistical viewpoint to address this $3 million question is estimate a whole exposure-response function non-parametrically. And we could do that because, remember, we create this new data set, right? And then we have a new data set, and then we can fit a non-parametric estimates of the exposure-response function. And you can see, actually, that this exposure-response function is actually a little steeper, a lower level than a higher level. This is why when you fit just a model, linear model, and you take a breakpoint, it's actually a lower level, the effect are a little higher. The other thing to really, this is the $3 million, more than $3 million exposure-response function. You can see that a level below 12 microgram per cubic meter is actually linear. Right? So what this is saying is that we need to reduce PM 2.5 as much as possible. There is really not a threshold. Okay, so are we done? No, of course not. There are a lot of problems what we have done before. And so this is why I thought this was a good story for this audience. Now, this approach is not Bayesian. Now, Fanley yesterday gave a great review of Bayesian causal inference. So why do we need to be Bayesian? And so that made me think a lot. So thank you, Fan, if you're here. And in this context, actually, we want to be Bayesian for several reasons. So one, I'm very proud of the work I'm going to tell you about it, because I think it's very rigorous from a Bayesian viewpoint. In addition of being able to quantify the uncertainty much better, remember the uncertainty around this exposure response curve is really important, okay? And ultimately also, the policy question is a change point question. Is there a change point in this exposure response curve? Is there a level of pollution below which there is no effect? Now, there is a tremendous amount of work on change point, also in Bayesian analysis, of course, but there is not much in the context of causal inference. Remember, I need to estimate this change point in exposure response function that has a causal interpretation, so after I have done my design phase. So this is work that is under review right now. If the reviewer is here, we are working really hard on this revision. So, just really hard, trust me. It's something I'm really, really excited. Again, I cannot take much credit about this, except of learning from my wonderful colleague. So here's what we did. Okay, so we actually showed that it's equivalent. Everything I told you, now we're doing in a Bayesian context, but we are using a Gaussian process to do the matching. Let me tell you what it means. So first of all, this is exactly the same question. What would have happened to those who were in fact exposure to level W1 of a pollutant if exposure has been a level W2? So I wanted to estimate this counterfactual outcome at any level of exposure. So really what I want to do is to estimate a causal exposure response function, okay? So E, the expected value of the potential outcome at every single value of exposure is this quantity. My quantity of interest is RW. So as I mentioned before, I'm going to put the slide again, is we want to match, the design phase of causal inferences, we want to do exact matching with using a generalized propensity score. In JAW work, in the previous work, what I told you is that we are really actually like manually creating this new data set where for every single unit, we match with respect to all of the covariate, with respect to the propensity score, and creating this new data set. Here, we do something different. We actually model the whole thing. So first of all, let me say we have our data set, our Y are the outcome, W is the exposure, which is continuous, C are all of my confounders, so we have a lot of observation, and Y is the potential outcome, a level of exposure, W with a covariate. We make all of the traditional assumption of strong unconfoundedness, consistency, overlap, and smoothness. I'm not going to go much into that. But this is the idea. So basically what we did is we modeled the potential outcome as a Gaussian process. So F is the function of the Gaussian process with a mean and a covariance function. I'm going to tell you in the next slide that the generalized propensity score and the matching are going to get baked in this covariance function. So basically, when I'm estimating the posterior predictive distribution of W, I'm going to borrow more information to estimating this potential outcome from the people that I need to match. So instead of doing exact matching, I'm just basically baking the matching into the covariance function of the Gaussian process. I'm going to tell you a little more what that means. So here is the idea. So basically, we first define a distance matrix between two units. And the distance matrix, which we call it D, it's a function of matching the unit based on their estimated propensity score, estimated generalized propensity score that is identified by E, W, C, and based on their exposure variable. And so basically, we purposely specify the covariance function in the generalized propensity score that has the matching piece as part of the off-diagonal element of this covariance function. And so basically, what that means is that we estimate the posterior distribution of my counterfactual outcome, YWC, that is based on sample I with similar exposure level and with similar values of the generalized propensity score. Now, the nice thing is that when you do this, you enter in the world of a Gaussian process and Bayesian, is that everything actually becomes simpler and easy mathematically, because basically, I'm not going to be able to tell you all of this property. Again, if you're one of the reviewers, they're beautifully described in the paper. But basically, the idea is that you have the posterior mean of this potential outcome becomes a weighted average of the observation where the weighting function, AI, it's basically developed to do the matching properly. So the similar unit, the twin sister of Jane, okay, will contribute much more in estimating the potential outcome for Jane than Richard, that has nothing to do, it's completely different from Jane. Okay, that's really the fundamental idea. And so the other really nice thing about this is, so my estimator, the Bayesian mean of my exposure response function, as I said, is a weighted average of the observed outcome. And so this value AI are really the one that basically borrow information from the twins and the cousin of the person that I want to match. The other really, really important element and feature of this work is that when you think about Bayesian causal inference, you have to think about the design phase and the analysis phase. And again, the design phase is about creating this match data set. And what we show in the paper is that, when you're thinking about this covariance function here, there are some tuning parameters. You see there is an alpha parameter and a beta parameter. This alpha parameter and beta parameter, if you were a Bayesian, you would put some prior in calculating a posterior. In Bayesian causal inference, as a funly remind us, it's different. I don't want to use the outcome to estimate these parameters. So what we do is actually, we estimate this parameter in a way that optimizes covariance balance. So in this way that we only use C and W to basically find the value of this parameter that break the correlation as much as possible. Because really, this is our objective, right? We want to do the matching, so we eliminate the correlation. The other really nice thing about being Bayesian in this is that I can calculate and articulate Bayesian inference or change point and uncertainty. So in the context of Gaussian process, oh my God, it's beautiful. It's so elegant because actually the derivative is also Gaussian process. So it's just like, oh my God, this is great. So basically, I wanted the definition of a change point is that there is whether or not there is a discontinuity in the derivative of the exposure response function. And so basically, we have a nice algorithm because with the Gaussian process, you can derive the posterior distribution of the one-sided derivatives in closed form. And so we can actually look at the credible interval of the left and right derivative and see whether or not there is evidence for a change point. And so basically how we do, basically we define the change point of an exposure response function as the places where a jump in the first derivative is present. We rely on the fact that the derivative of a Gaussian process remains a Gaussian process himself. We estimate the posterior distribution of the left and right derivative of the exposure response function. We found all of the non-overlapping intervals where the credible intervals of the derivative do not cover 0. And then within each interval, we identify the change point as the maximizer of the posterior mean of the derivative. So just to show you, this is just a simple example, a toy example that actually works. This is a simulation data. So you see that on the left, for a moment, just focus on the two panels on the left. The black line is the true exposure response function. So you see that we simulated in a way that has a lot of change points. The red is our estimated exposure response function using the Gaussian process and everything that we have recovered with the credible band. And then if you go on the bottom, these are the black are actually the truth in terms of where the change point really are. The red are our estimate. The blue bar are our candidate interval, and then we were able to identify this change point pretty much exactly. So now we have to, season 3, right? We have to redo everything. Now let's reanalyze the all-bloody database using a Gaussian process. So now we have a validation of whether or not the uncertainty was correct, whether or not there is a change point. The other thing which I'm not talking about here is, you have to think that when you're doing exact matching with hundreds of millions of observations, computationally becomes a nightmare. So what Boyu Ren, who is the lead author of the paper, has developed also is a computational efficiency approach, which is called the nearest neighbor Gaussian process for scalability. So basically, I'm just going to say that I'm going to match Jane with the first and second degree relatives, right? And I'm not going to look at the one that are very different from her, right? So when basically this way it's much more scalable, and I don't need to look for every single unit. I'm just going to look on the unit that are in the neighbor. So, and I'm sorry, this is what I was going to say, that on the right of this panel, we also look at the performance of the near neighbor generalized propensity score matching. And so it's computationally scalable. As you can see, we have a little bit of more issue in terms of smoothness, but we were able to identify the change point even when you're trying to really do a little bit of a shortcut to gain computational efficiency. So now we are applying this to the Medicare data. We purposely collapse the data into a zip code level by age, gender, and strata. So we have 520,000 samples. So 520,000 zip code. we had to use, here is a bummer here, right? There are a lot of work that needs to be done here. First of all, because it's a Gaussian process, so we just use the log mortality rate and assume it's Gaussian, right? So that's one thing. We'll see also, we can, I'm sure you will have a ton of questions about this, but also we assume that they are independent, they're really not. So I wanted to say this is the first way that we're doing the work, but there is much more that needs to be done. We use gradient boosting to estimate the generalized propensity score, and then we both analyze it with the nearest neighbor Gaussian process. So this is what we found. So on the left, this is the estimates, again, of the exposure response function using the Gaussian process and the 95% confidence interval. It's really nice to see that right now the WHO has set the national ambient air quality standard for PM2.5 of 5 microgram per cubic meter, and the EPA is setting it at right now at 12 microgram per cubic meter. So you can see that the exposure response function is actually pretty linear when you're going at the lower level. Now, on the figure on the right, these are the Bayesian estimates of the derivative. We identified some evidence of a change point of actually very low level, but not in the way that we were expecting, but actually in the way that say that the exposure response function is actually even steeper at a lower level, and there is a little bit of evidence of a change point at the higher level. What's really important also is if you'll see in the plot on the right how we were able successfully with the Gaussian process to really break the correlation. So this is the absolute correlation. One is the raw in terms of the observed data, and then the dotted line is the observed absolute correlation after we have done our matching with the Gaussian process and the generalized propensity score and the covariance metrics. And so you can see that we'll be able to adjust for measure confounding in a very way. So here we have proposed a Gaussian process that mimic a generalized propensity score matching algorithm for the estimation of exposure response function. There are a lot of very nice property, as you can imagine, theoretical property about all of this, including that we show that under certain condition is equivalent to the work that we have published in the Science Advance paper, and hopefully in JASA, that Zhao has done in a non-Bayesian way, but with the additional advantage that we can estimate change point, and we have a lot of very nice property. With the nearest neighbor approximation, the Gaussian process model is scalable to massive data set while preserving the correspondence to the generalized propensity matching algorithm. And the Bayesian framework, as we all know, makes the uncertainty characterization straightforward and enables the detection of change point. By the way, we are developing, and it's a process professional software package, both for the first version, the non-Bayesian version, and now the Bayesian version. So you can find it here, and so you can play, give us feedback, because I'm sure there is so much more that we need to do. Now, what's the impact of all of this work? So I think, on one hand, very good news that the WHO has lowered the national ambient air quality standard for fine particulate matter from 12 microgram per cubic meter to 5 microgram per cubic meter, and I'm proud to say this is a lot about the work that myself and my colleagues have done. And so this has been an enormous victory. Now, the Environmental Protection Agency now under the Biden administration, as we speak, is to reexamine the health standard for harmful soot. There is also something I want to mention, which I am not going to be able to talk about here now, but there has been an enormous amount of body of evidence, including from my own team, that have been shown for the first time a link between exposure to fine particulate matter, both from all sources and from wildfires, to increase the risk of COVID. And so, as you can see from this press report, this is also having a huge impact in lowering the national ambient air quality standard, because they actually mention here, in addition, a number of recent studies have examined the relationship between COVID-19 and air pollutants, including particulate matter, and potential health implications. So stay tuned, finger crossed, hopefully they're gonna make some good decisions. I just want to conclude that, of course, in 1 hour talk, or actually 45 minutes talk, there's so much more that needs to be done. By no means we have solved the problem. So there are huge issues on uncertainty quantification and propagation. Remember that when I started by saying we have this fancy machine learning model to estimate exposure to air pollution, well, it's estimated, right? So how do we propagate uncertainty? And again, that's applied to exposure to heat, exposure to tropical cyclone, and so on. I only talk about measure confounding, okay? There is a ton of work about, well, how you deal with unmeasured confounding, and if you're doing Bayesian causal inference or non-Bayesian causal inference, there's a lot of work, beautiful work that needs to be done. We developed a non-parametric estimation of exposure response curve in the context of causal inference. So sure, there is more. There is a fantastic amount of work going on, and again, it has been presented on this conference on thinking about heterogeneity of causal effect, right? So air pollution doesn't affect everyone equally. So I just show you a exposure response function, but then you can imagine that actually with this amount of data and with now the new approaches, there is opportunity to study heterogeneity of causal effect across the population. And then really important issues are reproducibility and open source, right? We always say it's very good to have to do reproducible research and open source. I have to tell you from my personal experience, it's very challenging to do it, number one, when you're dealing with several million observation, and number two, when you're dealing with an environment which is not about intellectual, but it's about politics and really trying to achieve a political agenda. So I just want to mention a work of my colleagues in terms of really thinking about causal inference and machine learning to assess health impact of air quality regulation, thinking about also multivariate outcome, right? I only talked to you about mortality, but we actually doing study thinking of every single cause of hospitalization. And so there has been fantastic work in thinking about both causal inference or not, in looking at the effect of fine particulate matter using considering a multivariate outcome. I talk about the matching work, and also there is now causal rule ensemble to basically build on the beautiful work by Susan Atey and Guido Imbens in thinking about interpretable inference for heterogeneous treatment effects. So what that means is, can we use machine learning and causal rule ensemble to identify the subgroup of the population that are more susceptible and more vulnerable? And that is really something really important. And finally, I want to mention the work on reproducible workflow. You can all imagine the amount of decision that we have to make from the raw data sources and linking, and so that is all work that fortunately is leading by Naheem, who's a software engineer, and really trying to have the full documented pipeline that is open source. So I just want to say that there are so many people involved in this fantastic work, and I'm privileged to learn from them every single day. So there are principal investigators from many institutions, wonderful postdoctoral fellow, PhD student, master student, and undergraduate students. So I just want to just show you some of photos of people not only at Harvard, but BU, Brown, Yale, Austin, Texas, and so on. So, and it's also really wonderful as we see the larger commitment of younger and younger students in really doing something that is very meaningful for society. So to conclude, the steps needed to mitigate climate change in the future are substantially the same as those needed to reduce the burden of health and disability to air pollution in the present. So cutting back on burning fossil fuel and biomass. So again, when we go back to my first $3 million question, if the Environmental Protection Agency decide, and let's keep the finger crossed, to go from 12, ideally to house the WHO's down to 5, what it means is that next year they're going to target the same sources of greenhouse gases emissions. So to me, this is, it's a huge, huge win. In the meantime, machine learning and data science allow us to measure exposure and pinpoint susceptibility and vulnerability. I've not talked about that, but trust me, there is a tremendous amount of work that we can do. And methods for causal inference, it's really now very natural to better disentangle causes from confounders, and therefore really provide more rigorous inference to inform policy in the context of air pollution, but also other natural disasters. So in my own perspective, looking ahead, I think that having developing new research data platform is key. Again, there is no data science without data, okay? And linking spatial temporal data on meteorology, climate, air pollution, land use, and satellite sensor readings to understand and quantify linkages to health indicator is a really promising area of research, and most importantly, to understand the distribution of effect on disadvantaged portion of the population. Thank you very much for your attention, and happy to take any questions.
I have two questions. First is, you mentioned census data. Which data source did you use, or was that me mishearing?
So for the confounders, we use census data, the American Behavioral Surveillance Survey, American Behavior Survey, and many others that are listed in the paper, and now I don't remember. But the census is one of the major ones.
Okay, I was just curious because if it was like the 2010 census, it'd be interesting if you could do a comparison between that and the demonstration file that uses the top-down algorithm, because if it makes your policy decisions change, then that's an argument on whether or not to implement that new data privacy methodology. So that was like one of the thoughts I had listening to that. And then my other question is more broad, and I think we're seeing more and more that our work is being used for politics, either for good or bad, and I'm just kind of curious if you have any advice for those of us who are working more in that public policy sphere of like, how do we handle that interpretation of our science, either for good or bad, and making sure that the right message is getting heard, but still not being so strained because of the political sphere? Yeah,
that's a great question. So number one, for the census question, by the way, you are absolutely right. And so we are looking, I don't know on top of my head, but we are studying and looking very carefully at which census we are using and how the estimates are sensitive to the different census. And that's why I want to show you like a huge team, because by no means it's only me. So yes, you're absolutely right. Now, gosh, I mean, your second question is hard. So I would say that what I do is, number one, I publish, okay? So first, you publish on the top scientific journal that you can. And so it's Science, Nature, New England Journal of Medicine. And then you speak on an authoritative voice based on what you have published. Now, you have no control on how that information then gets used and manipulated, and then there is not much you can do, right? So I think that my principle is, I try to have the best possible practice on what I can control. So in this way is open science, reproducible, publish in the best way possible. And then I also do speaking to the press. I think it's really important that we start speaking to the press and not be afraid of it. But when you're speaking to the press, you stick to the science, you stick to what you publish, and just stay with that.
All right. Now I have a follow-up comment. I'm sorry, I'm taking over the mic. Then would you think then maybe we should be doing trainings then on how we should speak with the press then? Because I work in a public policy institution and we do have training for that, but then that's not something like I got in grad school at all on like how to make sure that like, oh, think about sound bites and you have to be careful what sound bite, because if it's the wrong one, then journalists will grab onto that and completely misconstrue your science.
So when we publish one of these important papers with my student, I become really scared to them. Because what I say is, first we write the talking point, we have a Google Doc, we write what we're gonna say, that has to match exactly what is published. And then you don't answer any question that it's not based on the published data. And you just have to, you stick to the message that we write in the Google Doc. So yes, I do think that it's our responsibility now as educators, and having, I think, the work that we do, if you think about a lot of the bigger crises that we are facing in the world, can be addressed using data. And so I do think it's our responsibility to train the next generation not only to do the best possible analysis, but also to be able to communicate this analysis with the highest possible rigor, sticking to what they have published, and try not to, talk about blah, 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 right? So, yeah, I completely agree with you. I think it's something we really have to work better, to do better.
Thank you.
Okay.
Hi, thank you for the important and ambitious work. My understanding about propensity scoring is that it's there to protect you from model misspecification. You're using a GP here, which is a very flexible model, so that consideration sort of goes away. Could you get rid of the propensity scoring and just to use the GP to predict the outcome from the covariates and the treatment directly?
So when you're estimating so first of all, you're absolutely right that the goal of the generalized propensity score is overcome model misspecification to adjust for measure confounding. When you have matched your observation using the generalized propensity score, then you can use the generalized propensity score, as was discussed yesterday, in many different ways, also as including as a covariate into the model. We decided to have the best, I would say the most flexible way in terms of creating a new data set where we exact matching, because I also want to make sure that I can make sure that the correlation between each confounder and the covariate of interest in this Gaussian PM2.5, it's close to 0. So by doing exact matching via the generalized propensity score, instead of just sticking the generalized propensity score into the regression model, allow me to better see whether or not there is covariance balance. Yes.
Francesca, thank you. What a massive effort. Clearly, a massive effort that involves expertise in many different disciplines, right? Not just in statistics, both frequentist and Bayesian, but also in the subject matter domain and in public policy and the social sciences. And I'm thinking of the young investigators, young researchers, young graduate students that are starting on this on the very steep learning curve that they have in front of them to be able to tackle problems like this. And I'm curious about your thoughts as to how to guide that training to be able to do meaningful work that delves deep into so many different areas. Could you comment, please?
Yeah, I mean, it's a great point. I think it's, first of all, I think, what I've been showing here is also 25 years of work, right, that was coming organically, and so building a network over 25 years. So if you are a year one assistant professor, I don't think this is a bar that you should reach out. But I have to say that I think, there are a lot of mechanisms now for all the different institutions. I would say start very, very early. So if you're a statistician, you're doing Bayesian statistics, you're writing your Bayesian causal inference paper, you want to publish in JASA, all is great, but create a committee, an advisory board that it's interdisciplinary based on the fields that you have. And I think any institution can provide that. I personally really like the K mechanism, within the NIH for younger faculty, because the K99 R00 is a career advancement award, and I know you have the same for the NSF. This career advancement award, what's really nice is, in addition of writing down what you want to do, automatically it forces you to create a group of mentors. They're not, the expert on prior solicitation, but they're also expert in policy and climate, right? And so I think start sooner rather than later to really, have an interdisciplinary mentoring group that they can guide you. Because I think what's happening is often in our profession, and I've been seeing over and over, I've been extremely privileged to start my career at Hopkins with John Summit, who was the chair at that time of the Clean Air Act Advisory Committee. So I was trained from day one, and I was privileged and fortunate to know what are the right questions. Often what I see and breaks my heart is that there is a fantastic methodology and fantastic technical rigor, but that's not the question they want to know, right? And so this is why I think having an interdisciplinary mentoring, they can guide you from day zero and say, yeah, this is fantastic, but use this to address this, because that's how you're going to make the impact, and ultimately, also for career advancement, that's the most important thing.
Thank you.
Francesca, thank you. That was just splendid, absolutely splendidly comprehensive. I have two questions, or maybe a question and one comment on two different aspects of the talk. The first one is with Jane's twin sister. when you're actually going to look at or undertake these sorts of studies, one of the challenges is confidentiality, right? So where Jane's twin sister lives may not be available to you exactly, but you may know the region. But on the other hand, at least in some of my work, I've seen that PM2.5 and certain pollutants, they tend, even in low pollution areas, they tend to have a lot of diurnal variation spatially and temporally. And so I was wondering if you could comment on how that is taken into account in that study. I know you won't have time to go through all the details. The second is I was delighted to see you're using the NNGP for scalable Gaussian processes. So we have actually developed some work on that in 2016. But I was curious, I saw that you were using, I think, 500 neighbors. In our JASA paper in 2016, we showed, and there's some theoretical justification that you don't really need that many, even 10, 20, even if your big data is about 1 million, because it goes through this Vecchia's approximation, which has received a lot of traction, and there are many others who have worked on that. So that's just a comment. So I was curious why 500, but
yeah, well,
thank you.
Yeah, I don't have a particularly brilliant answer of why 500. I think we did sensitivity analysis, but thank you for mentioning that, because we should definitely look at your paper and look at that. So that's absolutely true. The first question you asked, you're absolutely right. So let me just say that for a moment. So we know Jane, we know every single Jane, every single person up to a zip code. Okay, so everything I said, just make for a moment this assumption, stick with me, that I basically assume that everyone in the same zip code breathe the same exposure level, which we know is not true. I mean, it's, PM2.5 is smooth, but as also I show you in this map, right, so you really point the finger on something really important here, because, yes, right? So, within a zip code, there is variation. So the other piece of work that we are doing, and I am learning from my PhD student and postdoctoral fellow, there is another area of research that we are doing, we are not talking about this, is how in causal inference you address issues with exposure error, right? So there is actually a lot we can do about that, because we have the variability within a zip code of how much exposure there is, we can build an error propagation of exposure within a zip code. Now, in causal inference, this is another thing that Fan didn't talk about yesterday. But in causal inference, when you want to deal with exposure with error in variable, it's not so straightforward. Why? Because if you have error in your exposure variable W, you're also going to have error into your generalized propensity score, because when you're estimating a generalized propensity score, you have an error there. Right. So there is, we publish I think we're going to publish, soon to be published, one of the first paper that tried to do error propagation in Bayesian causal inference to deal with this exposure thing. But again, this is another huge area that we need to do more, because again, Bayesian causal inference and error in variables, and Litz Stewart has done some of the work on that. It's really an important area of research. That's also another problem with this work, by the way. I mean, I'm assuming that the data is not imprecise, but clearly there is a lot of problem with that. But thank you.
Thank you.
Thank you. So, sort of like a philosophical question, but maybe with practical implications, would be that in a non-causal setting, we often look to predict well, whereas in causal inference, in a certain sense, you're trying to predict well not the real world, but the counterfactual world. No?
Yes.
And then based on that, you give policy recommendations. But then, after people implement these policies, they're going to look at what happens in the real world. That's it. You've told them decrease the pollution, and people's health is going to get better. But you're not going to observe that in the counterfactual world. You're going to observe it in the real world. The effects could be like 20 years from now, and many other things will have changed 20 years from now. So I'm wondering if you have any thoughts on how to reconcile, the predictive view, basically.
No, I mean, you're absolutely right. So when we're thinking about causal inference in the context of policy, There are actually, I think there are probably hundreds of buckets, but that's like two buckets. One is, what's the causal effect of an hypothetical change of an exposure from 10 to 12, which is all I talked about right now. The other way is to say, okay, we have implemented a policy. What has been the causal effect of that policy, right? And then also to predict what would have been the causal effect of that policy in the future, right? So let's make, number one, what I said is just one piece of big work. The second, I wanted to point it out, there is this paper that we published in JASA. The lead author is Rachel Natery, assistant professor in my department, where she tried to do something a little bit more similar to what you're mentioning, basically not predicting, but retrospectively, assessing the causal effect, not of an hypothetical change, but of a policy that's been implemented. And so I can see that what you're saying, that's really important to think about, which we can totally do now, to do projection and forecasting of what's going to be the potential benefit, not to hypothetically changes an exposure level within an exposure response setting, but really implementing this policy on this other policy. Many people have done that, but not in the context of causal inference that I'm aware.
Yeah, I'm thinking about convincing the policymakers. Like, they took an action, and if they don't see in the real world that this has had the intended effect, then maybe it loses credibility or something like that, right?
Yeah, absolutely.
Perhaps we can continue the discussion during the coffee break. Please join me in thanking Francesca again.
We need to work on the Gaussian process together. Absolutely. I'll look at it. Please do. Because this is the first work we're doing in the Gaussian process. Well, there is work for everybody. So, work for everybody forever. I'll let you check.
Le problème, c'est quand c'est du mauvais sens.
Check, check.